Google now. He used to write the Sun compilers. As a matter of fact, there's lots of compiler writers here. So if you've written code, you'll probably use some handiwork from these people. And you can read Lawrence's very brief biography in the textbook. He's got a long-term interest in parallel computation. One of the two most active people in the concurrency group in the standards committee. The other one is Hans Föhr, who's sitting over there. So if you're using concurrent programming in C++ for the next decade or two, you're heavily dependent on handiwork from this group.
Let's try something else. Yeah.
This is a talk about bugs, right?
Yeah.
It is.
These are not the bugs you're looking for.
It's someone thinking it's one of these are the bugs we're looking at.
Let's try something else. Okay, that will work. What I'm going to talk about today is sort of a personal history of the bugs that I've committed or encountered and the lessons I've learned from those things. And I hope you enjoy the talk. You should not expect anything terribly deep here. My first real program was a game. You have 7 pluses up on the paper terminal, and you can choose to take away either 1 or 2 of those pluses. And if you take the last one away, you lose. The computer is generous. You as the player get to go first. And our high school was having a little open house, people coming in, seeing the new computer, and the teacher picked my program to be on the demo and the open house. And that was really exciting. I mean, I barely started programming and already somebody was using one of my programs. People started playing this game and kept at it because they couldn't figure out why they kept losing. After a while, it suddenly dawned on them, the computer always wins. They were not happy because it was a game. They thought they could win and they couldn't. They were not happy. Now, these days of bug reports and all of that, I now have an answer I didn't have then. Not a bug. It's working as intended. But in fact, I was wrong because it's the expectations of the customers that tell us whether or not we have a bug. If we intended something that our customers think are a bug, it's a bug. So we don't get to define what our quality and what our bugs are. It's our customers. This thing showed up for me personally a little while ago. I was trying to do a backup on my home system, and it failed. So what did I get out of this? Just the failure message. You'd think backup should be something that should do its best effort, but it didn't. It just quit in the middle and gave me nothing. So In this sense, it's worse than a bug because it took my time away. But it said details. So I clicked on the details. Could not open file. Okay, it's a whole disk full of files. Which file? It wouldn't tell me which file. To this day, I have no idea why the backup, which file caused the problem, what was going on. I was never able to successfully complete the backup. And the lesson I learned from this is that diagnostics should be precise and actionable. You can't just tell people, I quit, because they don't know what to do. You need to give them enough of an error message so that they can take action to deal with the problem. And this is certainly not just Microsoft Windows backup that has this problem. This is all over the place. Could not connect to the network. Well, why? Disconnected. Why? Device busy. Really? What's keeping it busy? Cannot unmount drive. Please wait. As if waiting will close my window for me. So we need to be much more careful about how we address things, because working as intended is not an answer. My second significant foray was, again, another game. And the idea is you've got this airplane flying overhead, and you have an anti-aircraft gun, and you type in the angle of the gun that you want to shoot at, and the program tells you whether or not you hit it. And technically it worked, but my code looked like this. I tested the angle of every possible position on of the airplane. As a result, I had a lot of code. And then my teacher took a look at the code and said, you should know about this function. I had no idea that there was such a function there. So the lesson there is that you should understand your tools and not just take advantage of your limited knowledge and boldly go forth. I had this same problem arise a little bit later. I was asked to write a program to analyze a Boy Scout survey. And we were using an educational version of Fortran. And my main code I wanted to write looked like this. But this particular educational version of Fortran did not allow any array of more than 215 elements. I needed 5 by 5 by 72. And so my workaround was to break that out into 25 lines looking like this. Every time I wanted to access the array, I had 25 lines of conditional stuff. Fortunately, cards were somewhat easy to duplicate, but it probably would have been better had I known a couple more things. Functions and subroutines, again. But that was not the real problem. The real problem with this program was I got 7 survey responses back. So here I am, my program, the data to analyze. The lesson I learned from this is to make sure that I have a problem before I write the program. A bit later in college, we got a new VAX system, and it was big enough to handle a substantial load, and the director of the computer center decided that computing was important. He wanted everybody to have access to computers, so he gave everybody in the university an account. Every student, every faculty, every staff member, everybody had an account. That's 2,500 accounts on this VAX. And we got done bringing up those accounts, and logins took forever. The reason was, login did a linear search through all the possible users to see for a match. This was never a problem for the DEC developers because their systems never had more than a dozen people. But now with 2,500 users, it was a problem. And the lesson I learned from this is that excess computational complexity is in and of itself a bug. Problem surfaced a little bit later. I was working on a test system. And so you'd write a test program, we would compile it and run it on the test machine. One of its features was it had an unbalanced binary tree for its symbol table. And this was never an issue because programmers have a mix of identifiers. It was worked out reasonably well. Until somebody came in and wrote a program to generate a program. And the variables were V0001, V0002, V0003. And that turned our symbol table into a linear linked list. And we were back to the same problem. And the lesson I learned from this is that programs must handle extreme input. So you can't handle just the average case, you have to handle the extreme cases. Another problem we had on the VAX, print file.txt. You wouldn't think this would cause a problem, but when somebody printed the file, system load would go to 25% just printing that file. And the problem turned out to be that the way the printer driver worked is it would take a line of characters, shove them into the line printer's buffer, and then tell the line printer, okay, your line's ready, go away and print. And glacially, the line printer would print that line, come back and say, okay, I'm ready for another line. The problem was that the VAX was faster than the printer could accept characters into the line buffer. So the VAX would shove out a character, okay, shove out the second character, and the hardware would say, I'm not ready for you. So the VAX would say, well, if you're not ready, I'm going to do something else. So it would do a full context switch to something else. And then the line printer would say, okay, I'm ready for that next character. And it would do a full context switch back. So we had almost 2 full context switches for every character going to the line printer. They sent us a patch. They inserted 7 no-ops into the critical loop to slow the VAX down enough so that it would send out the characters. So I'm sitting here thinking, what happens when the next machine comes out and it's a bit faster? I wasn't around to find out. But what I learned is that open loop timing is fragile. I had this same kind of problem show up in grad school. We had this game called X-Tank. It was very interesting in that it would allow humans and robots in a multiplayer environment running in the same game. And that was all working great. And then we replaced a lot of our 68020 systems by Spark systems. The Spark was a lot faster. The problem is, robots became instant death because it was cycling through the game loop much faster than any human could possibly keep up with. And again, the open timing loops are fragile. So also, I was working on a parallel program. And 120 processors at the time was a huge machine. So any problem you get is going to be serious. And my program had an occasional failure in it. And just every once in a while it would fail. And many of you can see this coming. I had an improperly handled data race in the code. And I was never actually able to find this debugging. The only way I was able to find it is to read through my code very carefully, examining the code. So the lesson I learned from this is that you cannot debug all problems. That some problems you must design and review out of the system before they ever become bugs. But it wasn't that I didn't understand the problem or didn't think I was doing the right thing. The problem was here. I meant to do an equality test, not an assignment. So then I thought, well, I knew that. Why did I make a mistake? I mean, what's the real issue behind this bug? And it's actually a combination of three things. First, in C, assignment is an expression. So in Fortran, this never would have been a problem because the assignment is a statement. You can't use it in the context of a conditional. The second thing is that in C, there's an implicit conversion of integers to booleans, right? If I'd gotten a compile error saying an integer is not a boolean, this problem would not have happened. And the third thing was C had an unconventional use of operators. The equal sign is used for equality all throughout my entire school career until I got to computers. Only in computers did the equal sign mean assignment. And the lesson I learned from this is that our conventional wisdom that the feature test problem grows as n squared is wrong. It's actually much worse than that. So if we're going to introduce new features into a program, we have to think really deeply about how we're going to test it and how it's going to interact with all the systems. Because we cannot test the feature set. It's just too big. This same problem arose when I was porting my programming system to the Alliant FX. And it was dying. And I finally tracked it down to a combination of three things. I was using GCC's global register variables to store thread pointers. The FX was unusual in that it had a caller saves register protocol, whereas the other systems using the 68000 had a callee saves. And I was calling into FX system libraries. So my code was not saving the register because it was a global register variable. It's not supposed to save it. The system libraries were not saving that because the caller is supposed to do all the saving. And so they were tromping over it. So I did a lot of work to try and save my register. And my last bug was the bcopy routine, which was called implicitly in my code by structure copies. And so I needed to fix bcopy. What I did is I went into the debugger, had it print out the bcopy routine. I copied that into a source file, changed the registers it was using to avoid using my registers. I reassemble, relink, and run. It died. That was not good enough. After a little work, I figured out the problem was that the assembler out of the debugger, the assembly language coming out of the debugger, did not match the assembly language of the system. So the same mnemonic generated different size instructions. And so all of my offsets that I copied out of the debugger were wrong. And the lesson I learned from that is that the fidelity in your representation prevents a lot of problems. This fidelity problem has arisen recently. I was working on GCC, and if you have a tagless struct like this, GCC does something really kind of interesting. It makes up a unique name for that struct. Then it does a lookup to see if it's been defined before, which seems kind of pointless. And then sometimes later, it will pattern match on the identifier it made up to determine whether or not it was a made-up identifier and didn't actually have a tag. So the representation of these things has low fidelity. And it's working fine for regular compilations. But if you're trying to go in and use the compiler for some other purpose, this lack of fidelity in representation caused a problem. Going back in time a little bit, we had a graduate seminar class, and we wrote a multiprocessor operating system. And it all sort of came together at the last minute, but the last minute involved a lot of bugs. And afterwards, we were sitting around talking, you know, what did we actually learn from writing this thing up? And one of the things that we realized is that most of the bugs we had when we put the system together didn't happen between the people that were involved. They happened when one person wrote two modules that were connected together. So we had the same person on both sides of an interface. That person knew too much about either side and didn't actually have to think about the interface. The interfaces that were negotiated were much better understood and tended to not cause any problems. So if your interface is important, make sure it's negotiated, which means you have to put two different people on either side of that interface. The Palm PDA had graffiti to write with, and it also had, in many of its applications, an auto-capitalization feature. It would say, yeah, I know, you're starting a sentence, I'm going to capitalize. Or you're starting a field, I'm going to capitalize. The problem was that it didn't always do the right thing. And I found that correcting its automatic mistakes to be slow and frustrating. And the lesson I learned from that is that if your error rate is low, it's not good enough. Your program is broken. Your error rate has to be vanishingly small, or it's got a problem. I'm going to go into a little bit of work on the Sun. Talk a little bit about my first task when I joined Sun, which was to write the mangler and demangler for the first standard version of C++. And I've got several things to talk about here. And overall, the system didn't have that many bugs. And part of it was how I avoided them. And so I'm going to talk about that. The first thing I did is I made a single source for the documentation and the reference demangler. So I could not change the documentation without also changing the reference demangler and the reverse. So we caught a lot of problems very early on with this approach. And the documentation was always up to date. The other thing that made this work is that the reference demangler's interpretation was part of the test suite. So for every test, the reference demangler had an interpretation of what that meant. So now if I changed the documentation, there was a good chance I was going to break a test. And so I had to update everything when changes happened there. And the lesson I learned from that, because it was so successful, is that you want to automate if you want consistency. You need to automate your consistency checking. If you're relying on people to do it manually, it just probably won't happen. The other thing I did is I worked very hard to make sure that the output of the demangler looked like C++ source. And then I took the test case in C++, compiled that to object code, extracted the mangled names, ran them through the demangler, and then compared that back to the original source. Now, it doesn't always work because there are some things that you can say in a mangled name that you can't say in source. But it worked very well. We caught bugs very, very quickly early on because of the problem of this feedback loop in the system. The lesson I learned, when possible, close the loop on the tests because I caught bugs so early. So overall, the mangler and demangler had a pretty low bug rate, but they weren't entirely free of bugs. And in fact, we were getting close to release, and the mangling has an abbreviation feature to compress the mangled names, and I was a bit nervous about it. And I said, I need at least another day to test this. But too late, ship now. And sure enough, there was a bug in the abbreviation routines. Problem we had is we were shipping this. People were compiling it into binaries. If we fixed that bug, we would break compatibility. And breaking compatibility was not something we wanted to do. So we basically lived with that bug for the rest of the compiler's lifetime, which is still going.
Tell me about it.
So the lesson I learned here is never ever slack off on testing anything that affects the ABI. If it affects the ABI, you had better be sure that you have fully tested it. But that wasn't the only problem in the Mangler. In C++, and there's a bit of confusion about const array versus array of const. The rules are kind of tricky, and our compiler didn't quite get it right in the first couple of releases. But at one point, some guy went off and fixed it. But to fix it, he changed the internal data structures representing arrays. Well, the representation changed, so the mangling changed. But our test cases were not deep enough to detect that. So it wasn't for another 2 releases that we found out we changed the mangling. And now we're kind of stuck, because if we fix the breakage here, we'll reintroduce breakage over there. And so we just decided, okay, well, sorry, can't fix it. Try compiling again. What I learned from this is that the product is defined by your tests. If you don't have a test for a feature, it's not in your product. That feature doesn't exist. If you don't have a test preventing a bug, the bug is actually part of your product. So your product is defined by your test cases. So that's where you need to focus. Sometime later, the mangler was asserting in the middle of the compile. And on something very much like this. And the guy working on this came back with a code review to me, because I'd written it originally. I reviewed the code. And his solution was to look something like this. So if that pointer is null, just don't do that part of the mangling. My response was rather short. Because that assertion there was my understanding of what the data structure should look like. So I didn't think the mangler was actually wrong here, and I didn't think the mangler should be changed. And in fact, it turned out to be a user error. So the lesson I learned from this is that asserts actually encode the programmer's understanding of the state of the program. And so if you want to change an assert, you have to prove that the original programmer was confused. So changing an assert requires a lot more work than you might think about. So it was an undiagnosed user error. So why was the bug fix focused on the assert? Well, the reason was that assert was the symptom. And the fastest path to getting rid of the symptom was to remove the assert. The problem is we didn't dive into the root cause deep enough. Oops, sorry. We need to push through the root cause. It's not sufficient to get rid of the symptom. We have to push through the root cause. Now, Sun had, to its credit, a field in the bug database on the root cause. So we could have some of this information, but it was almost never filled out. There was no procedural mechanism to ensure that that field was filled out. To get a review, get that bug report reviewed reviewed by somebody else to say, yes, I believe that is a root cause and not just a symptom. So the lesson I learned from that is that software quality is a shared commitment. Everybody working on a system has to share a commitment to create a quality product through going the extra mile when a bug report comes in, to doing a careful review, to setting up procedures on how you respond to